Hello everyone. So in this video we are going to discuss about three important properties of continuous time Fourier transform. So we'll start with duality, then we'll discuss the Parseval's relation, and then finally we'll discuss the convolution property. So we'll start with duality. So duality states that if xt is having a Fourier transform of x of omega, then x of t, here it is capital X of t, which is will be having a Fourier transform which is equivalent to 2 pi of x of minus omega. So this is the property of duality. So how we can achieve this property? We can have to do some simple replacement in the expression for xt. So suppose we have xt which can be represented as 1 over 2 pi minus infinity to infinity x of omega e raised to the power j omega t d omega. So here we'll do a simple replacement of omega with t and t with minus of omega. So after replacement, what we'll get? We'll get x of minus omega, which will be equivalent to 1 over 2 pi minus infinity to infinity capital X of t e raised to the power minus j omega t dt. Now we'll move this 2 pi factor to the left hand side. So what we'll get? We'll get 2 pi x of minus omega, which will be equal to minus infinity to infinity x of t e raised to the power j omega t dt. And as you can see, the right hand side is the form for Fourier transform of x of t. So what we are finally getting? We are getting Fourier transform of capital X of t, which will be equal to 2 pi x of minus omega. So if you can see that by replacement of t with minus omega and omega with t, we'll get this expression of duality. So to understand the property better, we'll just do a small numerical. And why we are reading this duality property? Because sometimes it's very hard to get Fourier transform of certain signals. So duality help to get the Fourier transform of that complex signal in a very easy manner. So we'll see. Suppose we have given a function gt which is having a form of 2 over 1 plus t square, and suppose we want to get the Fourier transform of this expression. So using the traditional equation property, if we'll write the Fourier transform of this expression, then the calculation will be very complex. So what we can do here, we can use the duality property. So using the duality property, we can easily get the Fourier transform of this equation. So for that, what we have to do? So we have to consider a signal xt, which is e raised to the power minus mod t. Why we are taking this signal? Because the Fourier transform of this signal, that is x of j omega, is basically 2 over 1 plus omega square. So as you can see that the Fourier transform has same functional form as given by the signal g of t, only difference is the variable here. So one way to get the output is direct application of the duality property. So by applying duality property, what we can get? We know that xt can be directly written as 2 pi x of minus omega. So if we replace x of minus omega in this equation, then we'll directly get the Fourier transform of 2 over 1 plus omega square. So what will be the Fourier transform of 2 over 1 plus omega square? It can be written as 2 pi, and x of minus omega will be what? E raised to the power minus of mod of omega. So this is the Fourier transform of 2 over 1 plus omega square using the property of duality. And that can be done in, so in this way we can directly get this form. So if you want to get an insights of what is happening here, so we can do like this. So suppose we have e raised to the power minus mod t. So how we can write it? As 1 over 2 pi minus infinity to infinity 2 by 1 plus omega square e raised to the power j omega t dt. So here what is this? This is your xt and this is your x of omega. So now what we'll do? We'll replace t with minus t. So t is replaced with minus t. So what we'll get? We'll get e raised to the power minus mod t, which is equivalent to 1 over 2 pi minus infinity to infinity 2 by 1 plus omega square e raised to the power minus j omega t dt. Now we'll move the 2 pi to the other side, so we'll get 2 pi e raised to the power minus mod t, which will be equal to minus infinity to infinity 2 over 1 plus omega square e raised to the power minus j omega t dt. Now what we'll do, we'll replace t with omega. So here the second replacement come into the picture. So what we'll do t is replaced with omega. So we'll get e raised to the power minus mod of omega, which will be equal to minus infinity to infinity 2 over 1 plus t square e raised to the power minus j omega t dt. And as you can see, this is the form of Fourier transform pair. So the Fourier transform of this function can be represented in this form. So the Fourier transform of 2 by 1 plus t square can be represented as 2 by e raised to the power minus mod omega, and that we are getting directly from the duality property, though I just give you quick derivation to understand it better. So this was all about duality property. We'll now go for the Parseval's relationship. Hello everyone. So in this video we are going to discuss two properties, that is Parseval's relationship and convolution property. So we'll start with Parseval's relation. So we have already seen this relationship in case of our Fourier series. So now we will describe this in terms of Fourier transform. So suppose we have an xt and x of j omega. They are forming a Fourier transform pair. So this property states that summation minus infinity to infinity mod of xt square dt is equivalent to 1 over 2 pi minus infinity to infinity mod of x of j omega square d omega. So here this quantity in the left hand side denotes the energy in the signal, and the quantity on the right describes the energy density spectrum. So this describes the relationship of the Parseval's theorem. So now we'll see a small derivation how this expression can be verified. So we have our signal on the left hand side as minus infinity to infinity as mod of xt whole square dt. We can rewrite this expression as minus infinity to infinity x of t multiplied with x conjugate of t dt. Now we know that xt can be described as 1 over 2 pi minus infinity to infinity x of j omega e raised to the power minus j omega t plus j omega t dt. Then what will be x star of t? It can be described as 1 over 2 pi minus infinity to infinity x conjugate of j omega. Now it will be replaced to minus j omega t dt because of the conjugation operation. Now we'll replace this x conjugate t in this expression. So what we'll get? So we have our expression as mod of xt square dt integration minus infinity to infinity. It will be equivalent to minus infinity to infinity xt as it is, and we'll replace x conjugate t with the expression which we have got in the previous section. So that will be 1 over 2 pi minus infinity to infinity x conjugate j omega e raised to the power minus j omega t d omega, and this will be dt. Now we'll reverse the order of integration. So reversing the order of integration, what we'll get? We'll get an expression which is equivalent to minus infinity to infinity mod of xt square dt, which will be equal to 1 by 2 pi integration minus infinity to infinity x conjugate j omega. So this is your conjugate, and now due to reversal, what we'll get here, we'll get minus infinity to infinity xt e raised to the power minus j omega t dt, and this expression is familiar. This is equivalent to x of j omega. So what we'll get a multiplication of x conjugate j omega with x of j omega, and that will be equivalent to your 1 over 2 pi minus infinity to infinity mod of x of j omega whole square d omega. And on the left hand side, what we have minus infinity to infinity integration of mod xt square dt, and this is the relation which we have described in the first step. So this is the Parseval's relationship. So we'll also solve some numerical in the subsequent videos, but here we are just giving the statement, and when we do some numerical, then the concept of Parseval's relation will be more clear. So we'll move on to our next property, that is a convolution property. So convolution property is very important property, as it will help you to get Fourier transform of some of the complex functions in a very easy manner. So what this property states, that suppose we have an input signal to a system having a Fourier transform of s of x of j omega, and we have an impulse response h of t whose Fourier transform is denoted by x of h of j omega, then yt, that will output will be your convolution between h of t and x of t. This we have seen that why this is convolution in our previous video, and the output Fourier transform can be given by h of j omega x of j omega. So this is the property of convolution. So basically the convolution in time domain is equivalent to multiplication in the frequency domain. So this is convolution here, and here we are getting the multiplication. So now with the help of one example, we will able to understand this property in a better manner. So suppose we have a signal x of t which is represented by e raised to the power minus bt ut, and we have an impulse response h of t which is equivalent to e raised to the power minus at ut, and in both the cases b is greater than 0 and also a is greater than 0. So this is the input and this is the impulse response. So what will be the output? Output will be y of t which is equivalent to h of t convolution x of t. And as you can see, this is a very complex operation, and in time domain it is very hard to compute that. So let's use the convolution property to get the output of this system. So what we'll do, we'll take the Fourier transform of both the signals, and we have already derived the Fourier transform. So you can just directly write. So x of j omega will be equivalent to 1 over b plus j omega. And similarly, what will be h of j omega? H of j omega can be written as 1 over a plus j omega. So, and from the property of convolution, what property of convolution say? Suppose output is your yt, which is ht convolution of x of t. Then in frequency domain, what will happen? We will get x of j omega, which is equivalent to h of j omega multiplied by x of j omega. So here we have x of j omega and h of j omega. We have to just multiply to get the output. So y of j omega can be written as 1 over a plus j omega b plus j omega. Now this is the Fourier transform, the output. So in order to get yt, what we'll do? We'll take the inverse Fourier transform of this expression. So here we have to use the concept of partial fraction to get the inverse Fourier transform. So how we can do that? We can write y of j omega as a form of a by a plus j omega plus b by b plus j omega. So this is the partial fraction form. And from your basic mathematics, you can solve this expression by comparing with the original form of y of j omega. And what you will get, I'm just writing the final expression, what we will get for a and b. So a will be equal to 1 over b minus a, which is equivalent to minus b. And we replace in this expression what we will get. So y of j omega will be equal to 1 over b minus a, that is equal to 1 plus a plus j omega minus 1 over b plus j omega. So this is obtained by just replacing a and b in this expression. And this form looks familiar, so we have this Fourier transform as 1 over a plus j omega. So we know that the inverse Fourier transform of this expression is equivalent to e raised to the power minus at ut. And similarly, the inverse Fourier transform of this expression is equivalent to e raised to the power minus bt ut, and we are multiplying it with 1 over b minus a. So this is your expression for yt. So you have seen that we have getting the output expression in a very simpler manner by using the convolution property. So thank you.